Hello and welcome to this short overview of cryptography from the understanding and perspective of CS50. We'll go through the broad macro understanding and also some code level implementation of it. So cryptography, it's the art of concealing information. Like some of you may have done as kids actually, to pass messages on bits of paper in class, whether you might have mapped letters to numbers, or change the order of letters to codify these messages in order to hide its meaning. But whichever method you chose, there was an understanding on the other end of how to decrypt this codified message in order to obtain the true meaning. Such as this example we're looking at here. To the naked eye, which seems like gibberish, or nothing of direct meaning on first glance, but essentially it's encrypted information that when using the key or decryption key on this encrypted information, it can unlock or decrypt the information, and it actually says hello world. Some of you may see the key already, or code that would alter each letter to get at the real text that's hidden. It's just to decrement the letter to the one before it, or -1 letter index value, if you will. So I is H, F is E, M is L, etc. It's a very basic example, but does what it intends to, which is encrypt information, even though as easy as this may be to crack. Now down to some C code, we can look at how this can be implemented. So a character data type stores a single letter or symbol character, as you know, just any character on the keyboard. So some of you may have thought, how does a computer store a letter then? As you know, a computer uses binary, or ones and zeros essentially. So these characters get stored as binary numbers. Very crucial to understand this, that each character or symbol on your keyboard that is input into a computer is mapped to a binary number. This follows a specific mapping standard known as ASCII, a way to map a keyboard character to a number that the world can agree upon, so we can use these letters in computer programs. Now, since these letters or characters are essentially what seems to be a number in memory, it makes sense that we can use the number it represents, especially if each letter is in numerical order, as in A is 0, B is 1, and C is 2, etc. Although in ASCII, lowercase a is actually 97, and then B is 98, and C is 99. You can find the ASCII table online very easily and see what number is mapped to which letter. Now, using this print statement, you can see something very interesting. There's an integer placeholder, but I've passed in a character A. Now this compiles with no problem and gives me 97. The reason being is, as exactly as mentioned before, that characters are essentially decimal numbers underneath the hood, so we can treat them as such in context, and also by typecasting, where we explicitly tell the computer to interpret this information or this variable as a specific data type, or convert it to this data type, if you will. All we do to do this is specify which data type to typecast to in brackets before the data. So to change a character or char to an int, explicitly we can just use int in brackets before the character or variable, which is a char or character. And likewise, to change an integer into its corresponding character, just use char in brackets before the integer value or variable. Then you get them converted, and as before, chars and ints don't need typecasting specifically, since they are equivalent under the hood. It's just handy to know typecasting, especially for numerical data types, like converting floats to ints and ints to floats and vice versa. Now, reading this printf statement, we do exactly that without typecasting, passing in a C variable, which is a character, is a char, into two placeholders which accept a char and an int respectively. Now it will display the char and int values, that they are equivalent to. Adding this for loop makes it more interesting and is very informative. Since chars are numbers and they are in numerical and alphabetical order respective to each other, we can start at A and increment to Z, printing all the ASCII mappings from capital A through Z. Now you probably see how useful this is in manipulating information to encrypt information. And let's dive into that a bit more here. Now adding 1 to a character A does exactly that. It adds one decimal equivalent to the ASCII mapping of A, which is 65, giving us 66, which conversely maps to B. Now this method of encryption is known as a Caesar cipher, an algorithm which basically shifts the letter position up or down the alphabet with a given number, as in our initial example. Very easy. Now a Vigenère algorithm is more interesting. We leverage the numerical values of letters to use a word or phrase as the information to encipher with. As an example here, we use cat as the key, C-A-T, which we can encode to 3 numerical values of the alphabet. So C is 2, and you can say 0 is A, and 19 would be T. This is how many positions we're going to shift each letter in the text to be enciphered. So in Hello World, H gets shifted 2 places to correspond with C, E gets shifted 0 places to correspond with A, and L gets shifted 19 places up the alphabet to correspond with our T in cat. Cool. Not so obvious to the naked eye when looking at this encrypted or ciphertext. Now you can use this information of ASCII values and encryption algorithms to code your own encryption tool and decryption tool, passing in information and receiving back encrypted data, also known as ciphertext. If dealing with words, that would be considered ciphertext. Now these were the fundamentals of cryptography by locking up information using a key and an algorithm, and then being able to unlock it using the key. Just don't forget your key and go out there and crack it.